Hello again. Now I'm going to show pictures of these examples 3 and 4. You might remember, I've summarized it here. You might remember I had this matrix with repeated eigenvalues minus 1.5, but it was not minus 1.5 times the identity matrix. And this has eigenvalues 2 and 2, and it is 2 times the identity matrix. We compute the velocity vector v, in quotes, in both of these cases. Here the velocity vector was 3, 0, but here the velocity vector was 0 for any x naught. Okay, and we can get the solution in vector form, x naught plus v naught t times e to the lambda 1 t. And I can write that in terms of the two components like they want on web work. Here, since v is 0, that term goes away, and I just get x naught e to the 2t for any x naught. In fact, if I let x naught be the constant c1 and c2, you see that x1 is c1 e to the 2t, x2 is c2 e to the 2t. In other words, this is just 2 copies of dx dt is 2x as a scalar, and we know how to solve those by inspection. All right, let's look at some pictures now. So I'm going to share the screen. Okay, we have 2 copies here of the, 2 copies, come on, of the, of our website. And the first one, I'm going to look, first of these, I'm going to look at the vector field. So here's a vector field in the first case. There's only a one linearly independent eigenvector. 1, 0 is an eigenvector, and only multiples of 1, 0 are eigenvectors. The vectors everywhere else on the plane do not point towards the origin. And then when I look at the solution, well, let's look at the other vector field now first. That's compared to the vector field in this case. Here the matrix is 2i, and it looks like this a lot. Anytime there's a constant multiple of i, you see that every vector is an eigenvector. I've drawn 2 of them. 2 linearly independent eigenvectors are 1, 0, and 0, 1, but at any point in the plane, AV is just 2v. So every vector is an eigenvector with eigenvalue 2. The only vector, actually, the 0 vector, isn't an eigenvector. But other than that, every vector is an eigenvector. So now let's look at the solutions in these cases. We want to do systems. In the first case, we have minus 1.5 times x plus y. Is that the first component? And the second dy dt is minus 1.5y. Okay, and let's do that initial condition. We said 2, 3 was the initial condition we talked about. And let's use Runge-Kutta and submit that. So there's a solution that we got with a pencil and paper, or the whiteboard and marker. And let's think about what the others do. Every solution is going to approach the origin as t goes to infinity, because that minus 1.5 t is a decaying exponential, decays to 0. And you see what happens is the solutions are kind of trying to spin around. It's very close to complex eigenvalues with minus 1.5 plus or minus I times something small. Okay, but it doesn't quite spin around, but it has a little bit of that look. The other thing, there is a solution. If I say start at 2, 0, let's erase everything else. Let's start at 2, 0. You see that little red curve. It started there at 2, 0 and approached the origin. So if I start with the initial condition being an eigenvector, then I'll get v equals 0, because a minus lambda I times an eigenvector is 0. So if I start with the initial condition along an eigenvector, it goes straight towards the origin. But everywhere else, it approaches the origin, but along a curved path. That's to be contrasted with the second example. I had dx dt is 2x, dy dt is 2y. Right, that's clear. The curves. Yeah, here you see I can solve the x equation. X is equal to some constant, c1 times e to the 2t, y is c2 times e to the 2t. I start anywhere, I just go zooming exponentially away from the origin. Every vector is an eigenvector. And the solutions are just zooming away from the origin. This is a lot, by the way, like Hubble's law. The farther the galaxy is from you, the faster it's moving away from you, right? So this is a picture of Hubble's law. Let's see it this way. That's a little bit more like Hubble's law, so you can see that the farther you are from the origin, the faster you're going. All right.